Hi everyone, I'm Yuntao Wang from Tsinghua University. I will present our recent research around haptic feedback for VR, entitled MoveVR Enabling Multiform Force Feedback in Virtual Reality using Household Cleaning Robot. As more and more cleaning robots appear at our homes in recent years, the robotic vacuum cleaner becomes one of the most ubiquitous robots. We believe there are opportunities to leverage these domestic robots to conduct tasks beyond household cleaning. So we introduced MoveVR, which leverages household cleaning robots to provide force feedback for immersive VR experiences. We implemented MoveVR using HTC Vive Pro with two trackers tracking the user's hand position and HTC Vive controllers tracking the robot's position and orientation. We use Raspberry Pi 3B Plus to control iRobot Creative Tools movement. We used Alienware R5 laptop as the workstation to render the VR environment and match VR contents onto the robot, and configure the robot's movement in the space. To provide force feedback, proxies are required to deliver the force to the user. We used everyday objects and materials to make the proxy fabrication method more easily accessible. Three types of proxies are carry-on proxy that is carried by the robot, user-driven proxy that is held by the user alone, and a shared proxy that links the robot and the user. Components can be mounted to the robot using common adhesive tools such as touch fastener or tape. We designed for force expressions, including tension, resistance, impact, and material rigidity. This is achieved by changing the robot's movement speed, rotation, position, and carried proxies materials. Specifically, MoveVR can create continuously changing tension with an elastic strain between the user and the robot as a shared proxy. Different levels of tensile strength can be simulated by changing the distance between the user and the robot. For a given type of elastic strain and a particular surface that MoveVR operates on, there is a maximum tension force that the robot could apply to a user. It can be calculated by knowing the coefficient of friction, the robot's weight, and the distance between the user and the robot. Therefore, we can calculate the maximum length and pitch angle using Hooke's law to model the elastic strain. This will provide a guideline for future design on tension force feedback. Similarly, MoveVR enables multiple levels of resistant force feedback by configuring the robot's active status or the direction of the motion. MoveVR can simulate 3 levels of resistance forces on a specific surface where MoveVR operates on. Concrete resistance indicates static friction when the robot is locked in the place with the wheels placed vertically to the direction of the user's push. Heavy resistance means sliding friction when the motor is activated. Light resistance represents rolling friction when the motor is deactivated. We measured 3 types of resistance forces on 3 common surfaces shown in the table. MoveVR can also simulate impact force feedback and material rigidity. Different impact forces are generated by controlling the robot running into the human with different speeds, while material rigidity is created by replacing the carry-on proxy with different material objects. Lastly, MoveVR can also purposefully avoid contact with the user. We refer to this type of interaction as the invasive force feedback. To explore MoveVR's ability to provide multiple levels of distinguishable force intensities and directions, we conducted a force perception user study with 12 participants. The user study is to evaluate whether users can differentiate multiple levels of force feedback. To be specific, tension force feedback includes 5 directions and 4 tensile strength. Both resistance and impact force feedback include 3 levels of intensities. Material rigidity includes 5 classes using 5 different kinds of materials. Results show that users can perceive multiple levels of force feedback accurately. To further explore whether MoveVR can deliver more realistic and enjoyable VR experiences, we conducted a second user experience evaluation study. We compared our method with bare hand, vibrotactile haptic, and passive haptic solutions. We used the 7 points Likert scale to evaluate the realism, enjoyment, and easy to accept as the metric. We built a VR game, including 3 scenarios, within multiform force feedback were provided. The result shows that MoveVR provides a more realistic and enjoyable user experience when compared to commercially available haptic solutions, such as vibrotactile haptic systems, while having the advantage of scalability in applications when compared to passive physical proxy alternatives. To conclude, when comparing to existing VR force feedback solutions, our contributions have 3 forces. Firstly, for the first time, MoveVR enables multiform force feedback using a common household cleaning robot with easy fabrication and assemble methods using everyday materials, objects, and tools. Secondly, our force perception study demonstrates that MoveVR can enable rich force expressions with multiple levels of force intensity, force direction, and material rigidity. Lastly, our user experience study shows that MoveVR provides a more realistic and enjoyable VR experience. Thank you so much for your attention. Please refer to our paper for more details. You can also scan the QR code for my recent research updates.